All right, guys. Type 5s and Type 4 LSAs. Now, what I want to do is I'm going to focus in my topology on an area. Now, the area that I'm going to focus on, if you guys excuse me just one moment, I'll bring up my drawing software here, or try to. Toolbar orientation, just couldn't see it. I'll drag it up here to where I can get a hold of things as I need them. And what I'm going to do is I'm going to draw our topology in real quick. So in this scenario, these interfaces are operating in area 1, and we have another set of interfaces that are operating in area 2. So this is area 2, and obviously all of this is made possible by virtue of the fact that I created a loopback for area 0. Remember, if I have more than one area, I must have an area 0. Now what I'm going to do is I'm going to create a set of interfaces on R1. In fact, I'll write them out over here. I'm going to create interfaces that are going to be 10.1.0.1, 10.1.1.1, 10.1.2.1, and 10.1.3.1. And these are all going to be loopback interfaces. And they are going to exist on R1, so CSR1. And I'm going to use those for the purposes of redistributing prefixes into my OSPF configuration. So redistribution. So let's take a look at that from the command line. So let me get my marker here, so my pointer. And what I'm going to do is I'm going to create those interfaces. So we'll say config T, interface, loopback 100, IP address 10.1. Actually, you know what? I'm going to change these. We'll just use 1s instead of 10s. 10.1.0.1, 255.255.255.0. Interface LO101. IP address 1.1.1.1, 255.255.255.255.0. Interface LO102. IP address will be 1.1.2.1.255.255.255.0. And interface LO3 will be IP address 1.1.3.1, 255.255.255.0. And we should see those prefixes. So if I say show IP OSPF interface, actually show IP interface brief, we'll see those interfaces exist in my config, except I screwed up and used loopback 3. So let me fix that. I'll say config T, no interface LO3, interface LO103, IP address 1.1.3.1, 255.255.255.0. Exit, show IP interface brief, and we should see those loopback interfaces right here. Now what I want to do is I want to advertise these prefixes in such a way that they show up as external routes. Now the way that we do that is we do redistribution. All I'm going to do is I'm going to advertise them. I'll say router OSPF1, and I'm going to say that I want to redistribute connected prefixes, and there's another option here that I want us to use called subnets. Now that means that I want to advertise them with their variable length subnet masks intact. So I'll say subnets and hit enter, and that's pretty much all there is to it. So if I go all the way over here to R12, ping 1.1.1.1, I'm hoping that I'll have reachability to it. I had to do an ARP, and then the rest of the pings went. So we've talked about this process. Now I've got straight through. If I do a trace route to 1.1.1 numeric, we see we go from from R12 to R3 to R2 to R1. So everything's working exactly as I described. And what we want to do is we want to pay attention to how these prefixes are getting advertised. So from R12's perspective, show IP route OSPF, I'm now going to see a new route type. I'm going to see E's. And you'll notice that all 4 of these prefixes are being advertised as E2s. Now, interestingly enough, we see an external prefix here in the system as an E2 that's defined or describing 10.1.14.0/24. And that's interesting because my intention was to only advertise these 3 prefixes. And let me go ahead and advertise and fix these, because remember, we didn't do 0, we did 1. Okay? But I'm also seeing a prefix called 1,4. Now 1,4 tells me, that third octet tells me it's the link between R1 and R4. And the reason that it's showing up in my table is because on R1 I did redistribute connected. Now what that did is it said any prefix or any interface that is a physically connected interface on R1, I want to advertise it into OSPF. And it did. And since it was advertised using this redistribution construct, it was actually advertised as an E2 prefix. Now I don't want that. Right now all I want is I want to take these 4 prefixes, 1101, 1102, 1103, 1100, and 1101, 1120, and 1130, and I want to see those as E2 prefixes. Now what I want you to note is that these E2 prefixes are all advertised with an actual metric of 20. And the reason being is as a result of this redistribution process, that's exactly what happened. There is a default value called a seed metric. The default seed is going to be 20 in OSPF. And since these prefixes are E2s, that means that that seed metric is not going to be incremented. So at the time it was injected all the way over there on R1, it came through R2, through R3, through the tunnel to R12, and its metric stayed the same. Now if I wanted to alter that behavior, I could change the external type to an E1. And an E1 is actually going to be the seed metric of 20 plus all of the costs associated with every hop that it takes to get to me, for every device that it takes to get to me. Remember, we talked in the theory component that everything in OSPF is based on the principle of cost. What is the assigned value, lowest cost, to reach a particular prefix wins. Now, as we look at this, what I want to do is I want to really take the opportunity to play around with this for a little bit. So what I want to do is I want to look at where these prefixes came from. And what we're going to find is that these prefixes are actually identified via type 5 LSAs. And that type 5 LSA is going to exist everywhere. In fact, I want to highlight that point. So the way I'm going to highlight that is I'm going to come over here. I'm just going to erase all of this just to get it out of my way. I don't want to erase what's on the top. I got to stop drawing on my screens. Okay. And what I'm going to do is I want to take a look at a specific prefix. Now I'm going to use a command we haven't used in the videos yet. I'm going to type show IP OSPF rib, and I want to look at an entry in here for one of these E2 prefixes. So I'm going to pick one. I'm just going to pick this guy right here, 1.1.1.0. So 1.1.1.0, and I'm going to take a look at the output of this. Now what you're going to see here is, I love this table. It tells me the forwarding cost, what's the forwarding cost to get it to a particular destination. It shows me the cost as it arrived. It's going to tell me that it is an external type 2 prefix, that it is a /24 prefix. And it's going to tell me how I learned it. It's going to tell me I learned it from a type 5 LSA. that type 5 LSA described the network of 1.1.1.0, and it was actually originated on the area of, or in the area of 1. Now, when we look at what's going on here, we say it was learned via our tunnel. The next hop address that we learned is going to be 172.16.100.3, and this is flagged for a routing information base entry. So it's a control plane entry based on everything that we've talked about to date. Now, those type 5 LSAs exist everywhere. Let's go over to R1 and do the same thing. Actually, R1 is where it's connected, so we'll do it on R2. Show IP OSPF rib for 1.1.1.0, and when you'll notice we see pretty much the exact same thing here. So we have, it's a type 5 LSA. And when we look at the configuration for this type 5 LSA, it tells me it was originated by 1.1.1.1. Now, I said type 5 LSAs exist in my topology only because they're generated by a new OSPF router type. Now remember, we talked about ABRs, area border routers, devices that exist between multiple areas where one of those areas must be 0 and 0 must be contiguous, i.e. uniform across all of my topology and infrastructure. And we now see that we're going to be generating a new kind of prefix. Now I'm going to go to R1 for this. I'm going to say show IP OSPF database and look at the output here. And what we're going to see is notice that there are type 5 external link states for 1100, 11100, 1120, and 1130. It's also generating one for that 10.1.14. Now, let's take a look at this. Let's say show IP interface brief E assigned. And what we'll see here is that interface 1.4 is indeed operational. So what I'm going to do is I'm going to shut that interface down. Interface G2. And I'm going to say shut down. Now let's see if that actually basically extracts that from my table. So I'm going to go over here and I'm going to take a look at show IP OSPF, and now you'll notice that we don't have that prefix anymore. Now, since that prefix is on an interface that is shut down, it's no longer eligible to be able to be advertised. So that's normal routing behavior, nothing new. But what if I wanted to leave it up, but I still wanted to use the advertise connected prefix? So what we'll do is we'll go config T, and we'll say interface G2, and I'll say no shut. Now what that'll do is that'll put that prefix back in my routing table. So ultimately I should, once everything comes up and gets advertised, I should see 10.1.4 as an external prefix at some point. So I'm just waiting for it. So its state changed to up. We'll go back over here and let's just say show IP OSPF route, and we will see if it is there, and indeed it is. And again, it's because of that redistribution process. In fact, if I stop the redistribution process, router OSPF1, and I say no redistribute connected and take it out, those prefixes should disappear. There should be no external routes being advertised. And we see that there is not. In fact, I have no reachability ping 1.1.1.1 as a direct result of that being gone. Now I want to talk about the device that generates the type 5 LSA. Show IP OSPF border routers. And we see that we do have that ABR unchanged. Area 2, we're connected, we reach it via tunnel 0. The next hop to reach it is going to be 172.16.100.3, which is the VPN address on R3. We see it's being generated by 0002. Now I want to look at the type 5 LSA. So what I'm going to do is I'm going to, instead of just advertising everything, to keep things simple, I'm going to pick a single interface and advertise it via redistribution. So what I'm going to do is I'm going to write a route map. I'm going to say route dash map and we'll say test, and I'll say permit 10. I'm going to say match interface loopback 101 exit. Now what I'm going to do is I'm going to go to router OSPF1 and redo my redistribute command. Redistribute connected using the route map TST, and I'm going to say subnets. Now I'm going to also take the opportunity of modifying the metric. I'm going to say seed it with a metric of 100. Remember, the default metric was 20. So I'm now seeding it with a metric of 100, and it's going to have to pass through R2, R3, through the tunnel connecting all the way to my DMV connected remote sites of 10 through 12, and we'll see that that metric will remain unchanged. But I'll now only have one external prefix in my topology, and notice I do 1111. Now my ping will work. So if I come over here and I ping 1111, and it's because I have that type 5 LSA. I'm going to say show IP OSPF database, and I'm going to say I want to look at the external, and hit enter. There will only be the one, and we see here that we have a type 5 external link state advertisement, and we see that the advertising router is 0001, which is R1, and we see that that metric that was advertised is 100, and we'll get into some of these other details when we come up with designs that are going to have more than one exit or more than one entrance into an area. But right now I'm content with this being a good explanation of what it is we're looking at. Now I can get to it. So if I say trace route to 1.1.1.1, I can get to that. I know I need to go to R3. From R3 I go to R2. From R2 I go to R1, and then I'm delivered where this particular prefix actually exists. And it is being advertised as a type 5 LSA, like I said. But if I say show IP OSPF border routers now, we're going to see a new type of device. Notice it says that 0001 is designated as an ASBR, an Autonomous System Boundary Router. It exists in Area 2 in this particular scenario, and it is going to be SPF 22. Now, that's shortest path first. That's the number of computations that's actually been done. So if I were to come over here and say clear IP OSPF process, yes, wait for the process to come back up and take a look at the specifications here. We see that I really don't have any changes. I didn't wait long enough for anything to happen, and these are local shortest path first computations. Let's go back over to whichever device it was that I did this on, and I show IP OSPF neighbors. Alright, yeah, we're back up in full. Alright. Now I'll do the same thing here. I'll say clear IP OSPF process. Yes. Loading to full. Border routers, and you'll see there's been a local recomputation. However, not much has changed. Now the scenario here is notice that the ASBR is 10001. Now 001 exists all the way over here in area 1, but notice the area here says area 2. Well, that's because of reachability. Now we need to talk about this. So when I look at my table and I say show IP OSPF database, I'm going to see my type 5 LSA. Now my type 5 LSA is a very interesting LSA because again it's generated by an ASBR. But That ASBR is all the way over here in a completely different area, area 1. I'm all the way over here at the very, very far end of area 2. And it's going to say that the advertising router is 0001. Now what I want to do is I'm going to go up here and look at my Ospf database. So this is everything. Here's my type 1 LSAs. Notice, do you see a link in here for 001? And the answer to that question is no. In fact, the only thing that we see in here are going to be things that are in our area, because these are type 1 LSAs, and type 1 LSAs only travel inside of our autonomous system. The net summary link LSAs, those are simply being advertised as a direct result of the fact that I created a broadcast environment on my tunnel interfaces. So that's just saying, hey, for reachability, send it to R3. R3 can get it to every one of the devices because it has a peering with OSPF with each of those devices. And we have our summary netlink LSAs, which are type 3 LSAs. Notice in this scenario, I see an entry in here for 10.1.12.0, 183.1.1.1, 183.1.2.2, and 183.1.222.222, but I don't see anything in here identifying the advertising router of 0001. However, if we look at this entry right here, the summary ASB link state, notice you see a network ID, and it's saying to get to 0.0.01, send it to R2, which happens to be the area border router between areas 1, 2, and 0. So the primary thing to understand here is that the type 5 LSAs are generated by the ASBR. But outside of an area, I need to be able to provide reachability information as to how to get to the type 5 source, to the ASBR. And this is saying, hey, I need an exit point from my area, and I'm going to send traffic to it because it knows how to get to this router ID or this link ID of 0001. So type 4 LSAs and type 5 LSAs come together. However, there is a caveat to this. Type 5 LSAs are generated by the ASBR, the device where redistribution takes place. The summary Autonomous System Boundary Link State LSA, or the Type 4 LSA, is generated by the ABR between where the ASBR is and subsequent networks. Now in this topology, I only have 3 areas, 1, 2, and 0. Now when we look at this from the perspective of implementation, keep in mind that there are no routing table entries generated by this Type 4 LSA. However, it's important to note that in Area 1, there will be no Type 4 LSA. Let's look at that. If I go to Area 1, so I'm in CSR 1, that's the furthest that I can get, and I type show IP Ospf Database and hit enter, what we're going to find here is that I only have Type 5 LSAs, Type 3 LSAs, and in this instance, only Type 1 LSAs because I am actually restricting the generation of Type 2s. So why do I not need a Type 4 LSA? Well, I don't need a Type 4 LSA because it's saying the advertising router is 0001, and if I look at it all the way up to my Type 1 LSAs, what you're going to see here is I have an entry. So I don't need a Type 4 LSA inside of the area where redistribution takes place. Type 4s and Type 5s go everywhere by default. And it's important to keep in mind that the Type 5 is generated where redistribution takes place, whether I do it or it happens dynamically, and we'll get into that shortly. And the Type 4 LSA will be created by ABRs. So let's go back to the topology and let's put the rest of that information in. So right now I'm just going to grab my eraser, and what I'm going to do is I'm just going to take these question marks out, and what we're going to do is we're going to look at this from the perspective of what generates what. So type 5 LSAs are generated by autonomous system boundary routers, and type 4 LSAs are actually going to be generated by area border routers. And the job of the type 4 LSA is to tell everyone how to get to the ASBR inside of an area. So keeping in mind the way things have been working, we have type 1 LSAs that stay in the area. Type 2 LSAs stay in the area. So every one of these areas, actually, you know what, I'm going to color code these just for the sake of talking points. So let's see, type 1s. So this area's type 1s go nowhere other than this area. Area 2's type 1s only travel inside the area. And I'll go ahead and get this out of here. Area 1's LSAs, type 1 LSAs, stay inside the area. So do type 2's. So I'll go ahead and put those in here, since that's the ones we're talking about. Actually, I need green. So type 2's are constrained to the area. Type 2's. At the boundary of each of these processes, the ABR is going to actually translate and send type 3 LSAs, which go everywhere. So a type 3 LSA appears here, type 3 LSAs appear here, type 3 LSAs appear here. And we also have to keep in mind that when we do this process of redistribution, we generate a device where the redistribution takes place called the ASBR. And that ASBR creates type 5 LSAs that go everywhere by default. So they'll appear in every area. And it is also equally important, go ahead and just draw the third leg of this. It's also equally important that when an area where redistribution takes place, like area 1, knows the ASBR is here, it knows that these devices inside of these other areas lack information as to how to or where I send data that needs to go to a particular ASBR. What's going to end up happening is we're going to have these type 4 LSAs. And the type 4 LSAs are going to appear everywhere by default except in the area where redistribution takes place. And the whole rationale behind that is that we don't need a type 4 because reachability inside of the area is actually going to be resolved by the type 1 LSA. So this is the way things tie together. This is the importance of understanding how things work and how things function. And we've covered the type 2. We've covered type 1, type 2, type 3. We've just covered the type 5, which is the external prefix. So wherever I have a type 5 LSA, I am going to have an external prefix added to my routing table. The type 4 LSA will never describe a route. It only provides information as to how to get to the ASBR, which is going to be the device that originates a type 5 LSA. We also should have noted, and I'll highlight it, is that by default, all prefixes go into the system via redistribution as a E2, an external type 2 route. External type 2 routes are going to be seeded. They're going to be assigned a metric. So that metric that gets assigned is going to be 20 by default. I seeded mine with 100 to demonstrate that by default a external type 2 prefix does not increment. So it doesn't get modified as it gets advertised throughout the infrastructure. A type 1 does. So an external type 1 prefix is going to be 100 plus whatever is going to happen as it goes through, and you'll actually be able to see how that process gets modified. And how do I do that? Well, I do that at the point of redistribution. So let's look at the output on our device. And what we'll do is we'll wrap up this video real quick. And I want to illustrate the fact that I redistributed, so show run section router and hit enter, I did a redistribution and specified a metric of 100 and said that it was going to be the default external type. So if I go all the way over to R12 and I'd say show IP route for OSPF and look at the outcome here, I see the single prefix. Notice its metric is still 100. It did not increment. It traveled through 1, 2 devices and an overlay to get to me, and its metric stayed the same. If I modify that process, if I come in here and say config T router OSPF1 and I grab this entry right here and I say metric type 1, that's going to change the rules. Because by changing it to a metric type 1, I'm saying go ahead and add all of the costs in the path as you advertise the prefix. So now if I come over here and take a look at the show IP OSPF, notice it is an E1 metric, and now it went from 100 to 1,102, and that's a direct response to this tunnel. So let's take a look at R3 and see what it says. So before we didn't have an entry here, so I'll say show IP route OSPF, and what we'll see here is that I should have an E1 prefix, and notice it's 102. So that tunnel cost me, added a cost of 1,000 points, or 1,000 cost values onto that prefix as it was advertised down. And what we'll find here is every device in the data path, at the end of the data path, show IP route OSPF, is going to have the same metric assigned to it, 1,102, 1,002, so 1,001. So that tunnel is actually costing me a lot to set up. And the reason being is it's not a direct link. That tunnel's behavior is going to be dictated by the individual member interfaces. And OSPF has been configured out of the box to recognize that process. So the question is why would I be concerned with an E1 versus an E2 prefix? And in circumstances like what we have here, we wouldn't. The reason that I say that is that we only have singly connected areas. But if I had an area, let's say area 1, that had multiple ways of sending traffic to another area, it only stands to reason that I would want to take the path that has the least cost. As an example, if I left my E2 prefixes in place, I could actually do things like load balance using equal cost multipathing in a fashion that would actually be detrimental because the underlying path may not be equivalent to get to an ABR to get traffic out of my overall infrastructure. So the whole goal here was to walk through this idea, take us from type 1s, 2s, 3s, all the way up to the new topics that we've been discussing, type 4s and type 5s. Type 5s are ASBR advertised, so the device where redistribution takes place. Making a mental note that it's going to take place where I say it needs to take place, or it's going to take place where it's going to be redistributed automatically. Now that should immediately perk everybody's ears. Whenever I start talking about automatic redistribution, that's kind of a scary concept, but it does happen, and we're going to find out about it when we look at this idea of a type 7 LSA. And that's going to come in a video, well, actually 2 videos from now, because I do at least want to require a conversation about type 6. In fact, I'll go ahead and tack that on right here. So the next video will be a type 7 LSA. A type 6 LSA is an LSA that was used to correspond to something called the M bone, the multicast backbone. And the idea was that I could take OSPF devices and connect them in such a fashion that they could exchange multicast information using the OSPF protocol directly. However, it was never implemented. But there was the idea of a type 6 LSA. In fact, the only command you're ever going to use in OSPF, as I mentioned in class, is going to be the type 6 ignore. So the question now is that what we've done is we've specified an area, and what we've done is we've done redistribution in this area. We've generated a type 5. Inside of that area, we did not need a type 4, so we could use the type 1 LSA for reachability information. However, as that type 5 hit CSR2, CSR2 actually advertised the type 5s, but knowing the areas other than where the type 5 was originated, we'll need to know how to get to the ASBR. It says to get to the ASBR, 0.0.0.1, send it to me, 0.0.0.2, and that provides the reachability information necessary for everyone to be able to hit that ASBR. And that covers type 4s and type 5s. Just keep in mind that by default they travel in all areas unless we utilize some of the special areas that we still need to talk about. And we really can't talk about this next area, this next LSA, until such time that we talk at least about one area type, and that's going to be what we refer to as a stub area. Now, stub areas are very, very interesting because a stub area says I don't need to learn any type 5 addresses. And since I don't need a type 5 address, don't even bother sending me a type 4. So we're going to look at that, and we're going to stay with this particular configuration. But what I'm going to do is I am going to demonstrate how I can take area 1, leave it the way it is, and make modifications in area 2 such that area 2 is going to ignore these type 5 LSAs. All right, so let's see how that magic happens in the next video. So until then, I would suggest you guys go through this. If you have the least bit of confusion, do not move further, because every one of these concepts builds on top of one another. So with that being said, I will see everybody in the next video.